Hello everyone, myself is Dr. Vinay Kumar PN. I'm a faculty of mathematics from Sri HDD Government First Grade College, Padavalahipe. Today we are going to learn about Euler's theorem and Euler's extended theorem on homogeneous functions. Before entering into the theorem, let's learn what is meant by homogeneous functions. A function f of xy is said to be a homogeneous function of degree n if it can be expressed explicitly as a function of y by x into x to the power of n, or it can be expressed as a function of x by y into y to the power of n. Then we say this is a homogeneous function of degree n. For example, suppose f of xy is a function x square plus y square. Here, the highest power of x is 2. So, let us take out x square outside. If you take out x square outside, then it becomes 1 plus y square by x square, wherein we can write this one as x square into 1 plus y by x whole square. So, this is explicitly a function of y by x into x square. Therefore, the given function is a homogeneous function of degree 2. Let's see the other example. Suppose the given function is x plus y square. Now here, the highest power of x is 1. So let us take out x outside, so that this becomes x into 1 plus y square by x. No way we can write this one as a function of y by x, because here the power of y is 2 and here power of x is 1. We cannot merge this one so that this becomes a function of y by x. Hence, this is not a homogeneous function. By the same way, you can write this one as a function of x by y. How? By taking highest power of y in this one, then this becomes y square into x square by y square plus 1. So that this becomes a function of x by y. That gives you, it is a homogeneous function of degree 2. But you can apply any one of them and you can show it whether it is, you can verify it whether it is homogeneous or not. Now, let's move on to Euler's theorem. The statement of Euler's theorem is, suppose if u is a homogeneous function of degree n, then we have to show that x into partial derivative of u with respect to x plus y into partial derivative of u with respect to y is equal to n times the given function u. Let's prove this one. See, they are given u is a homogeneous function of degree n. And by the above definition, we knew that if it is a homogeneous function of degree n, then we can write this one in the form x to the power of n into phi of y by x, or y to the power of n into psi of x by y. Let's write u as x to the power of n into a function of y by x, and let's call this one as 1. Now, we need here dou u by dou x and dou u by dou y. Let's partially differentiate this with respect to x and y. What is the partial derivative of u with respect to x? It is dou u by dou x. And when you are differentiating with respect to x, this term also contains x and this function also contains variable x. Therefore, we have to apply product rule. So let's keep x to the power of n as it is. The derivative of phi is phi dash. Now forget phi. The variable is y by x, and we know that when we are partially differentiating with respect to x, your y should be treated as constant, so y will remain as it is. Now remaining variable is 1 by x. What is the derivative of 1 by x? Minus 1 by x square plus, now keep the second function as it is, phi of y by x. Now differentiate x to the power of n. The partial derivative of, the derivative of x to the power of n with respect to x is n into x to the power of n minus 1. Now here, if you send x squared to numerator, that becomes x to the power of minus 2. Here also there is x to the power of n. Since they are of same base, we can add the power. so that you will get x to the power of n minus 2, and there is one minus sign with y, so minus y into x to the power of n minus 2 into phi dash of y by x, that is your first term, plus n into x to the power of n minus 1 into phi of y by x. Let's call this one as equation 2. So your dou u by dou x is this. Now, similarly, partially differentiate this with respect to y. So, what is the partial derivative of u? The partial derivative of u with respect to y is dou u by dou y, which is equal to. Now, here, when you are differentiating with respect to y, your x should be treated as constant. So, your x to the power of n will be kept as it is. Now, this is the only term which contains y. So, what is the derivative of phi? It is phi dash. Then, forget phi. Now, the variable is y by x. And we know that 1 by x is constant. Forget it. Keep it as it is. Then what is the derivative of y? The derivative of y is 1. So we are going to get x to the power of n into phi dash of y by x into 1 by x. Now send this x to numerator. That becomes x to the power of minus 1. And since these two are of same base, we can add the powers so that you will get x to the power of n minus 1 into phi dash of y by x. That is your dou u by dou y. Now, we need to show that x into dou u by dou x plus y into dou u by dou y is equal to this. Now let's consider the left hand side, that is x into dou u by dou x plus y into dou u by dou y. X into, we know that from equation 2, our dou u by dou x is this much. Let us substitute it. Plus y into dou u by dou y is this much. Substitute it. Now multiply this throughout by x. So x into this. Because here x to the power of n minus 2 is there, and you are multiplying this by one more x so that we can add the powers because of their bases are same. So you will get n minus 2 plus 1, which is n minus 1. So minus y into x to the power of n minus 1 into phi dash of y by x. That is your first term. Then x into this. Again you will add the power n minus 1 by 1. So that becomes simply n. So n into x to the power of n into phi of y by x. Plus you are multiplying this by y, so you will get y into x to the power of n minus 1 into phi dash of y by x. But these two are one and the same with opposite signs, therefore they get cancels. So we left out with n into x to the power of n into phi of y by x. But we know that from 1, x to the power of n into phi of y by x is nothing but u. So we can write this one as u. Therefore we get x into dou u by dou x plus y into dou u by dou y is equal to nu. And this completes the proof. So the Euler's theorem says whenever your function is homogeneous, then we can write in this form. Remember, here n is the degree of homogeneous equation. Now we can extend this one. See, here we have considered two variables. Now similarly you can extend this one for three variables. That is three independent variable x, y, z. Suppose u is a function of x, y, z and it is a homogeneous function of degree n, then by the same lines as we proved for two variables, we'll prove this one for three variables. X into dou u by dou x plus y into dou u by dou y plus z into dou u by dou z equal to nu. You can verify the proof very easily. Now let's move on to next, Euler's extended theorem on homogeneous functions. What is that? If u is equal to f of xy is a homogeneous function of degree n, then we have to show that x square into dou square u by dou x square plus 2xy into dou square u by dou x dou y plus y square into dou square u by dou y square equal to n into n minus 1 into u. In the first theorem we have proved this. X into dou u by dou x plus y into dou u by dou y is equal to nu. See, if you write this one as simply x into dou by dou x plus y into dou by dou y of u, and if you square that, then you are going to get x into dou by dou x plus y into dou by dou y whole square, and expand it. Then you'll get x square into dou square by dou x square plus 2xy into dou square by dou x dou y plus y square into dou square by dou y square of u. So in that manner you can remember this one. And right hand side is n into n minus 1 into u. Let's prove this one. Since they are given u is a homogeneous function of degree n, and we know that we have already proved Euler's theorem is true for this. Therefore, I can apply Euler's theorem for this. So by Euler's theorem, x into dou u by dou x plus y into dou u by dou y is equal to nu. Now, partially differentiate this 1 with respect to x. Now, here x and dou u by dou x, both are involving the variables x. Now, you are differentiating with respect to x. Therefore, your y should be treated as constant. Now, apply the product rule for this. Keep x as it is. What is the partial derivative of this with respect to x? Again, you will get one more dou by dou x in front of this. So, dou into dou square, dou u, that is dou square u by dou x into dou x square plus, now keep second function dou u by dou x as it is. Partial derivative of x with respect to x is 1. So, simply you will get dou u by dou x plus y is constant. I'll keep that one as it is. Partial derivative of this with respect to x, that is dou by dou x of dou u by dou y, that is dou square u by dou y dou x, and n, right hand side, n into derivative of this is dou u by dou x. But remember, in the case of homogeneous function, whether you are going to write dou square u by dou x dou y or dou square u by dou y dou x, doesn't matter, they are one and the same. So whenever such a situation comes, you can straight away write dou square u by dou x dou y. Now, we'll send this one to that side. We'll keep only these two terms in the left side, so that this becomes n into dou u by dou x minus dou u by dou x. In these two, dou u by dou x is common, so we left out with this. Now multiply this equation throughout by x. So we are going to get, why we need to multiply? Because in the answer there is x square. We are having x only here, so that's why. Now if you multiply this by x, x into x, x square, dou square u by dou x square plus xy, dou square u by dou x into dou y is equal to n minus 1 into x into dou u by dou x. Let's call this one as equation 2. Now, partially differentiate equation 1 with respect to y. Since your x is constant, when you are partially differentiating with respect to y, we have to keep x as it is. We have kept. Now, partially differentiate this with respect to y, so that you will get dou u by dou y into dou x, dou square u by dou y into dou x. But we know that that is one and the same as dou square. Actually, this should be dou square. Dou square u by dou x dou y plus partial. Now here you need to apply product rule. Let's keep y as it is. Partial derivative of this with respect to y is dou square u by dou y square plus dou u by dou y. Let's keep that one as it is, into partial derivative of y with respect to y is 1 is equal to n into partial derivative of u with respect to y is dou u by dou y. Now as we know, you have to make the change. This is dou square, this is dou square, x into dou square u by dou x dou y plus y into dou square u by dou y square. Keep that one as it is. Send this one to this side, and in these two, dou u by dou y is common. Let's take it down. Then you'll get this much. Now multiply this throughout by y. In all these, make a correction. It is dou square u by dou x dou y. Now multiply this by y. Why you need to multiply this by y? Here we are having y, but in the answer we need y square. That's the reason. Now if you multiply this by y, y into x into dou square u by dou x dou y plus y square into dou square u by dou y square into n minus 1 into y into dou u by dou y. Now adding equation 2 and 3 gives you x square into dou square u by dou x square plus xy into dou square u by dou x dou y plus xy into dou square u by dou x dou y plus y square into dou square u by dou y square. That is left hand side with left hand side is equal to this plus this. In these two, n minus 1 is common. Let's take it out, so that you will get x into dou u by dou x plus y into dou u by dou y. And here it is 2 times. Remember, you have to replace in this case dou square u by dou x dou y. There is a slight mistake here. So if you add up these two, 1 time plus another time, 2 times, so that your x square into dou square u by dou x square plus 2xy into dou square u by dou x dou y plus y square into dou square u by dou y square equal to n minus 1 into this. But we know that by Euler's theorem, this is nothing but nu. So if you substitute, then you are going to get the complete result for Euler's extended theorem. This completes the proof. Now let's move on to problems on these. Let's solve some problems on these theorems. Now, the first problem is verify Euler's theorem for the function u is equal to x square plus y square. It's very simple. We knew that if we want to verify Euler's theorem, first we have to check the homogeneity of the given function. So let's verify whether the given function is homogeneous or not. Already we have verified this one and we have proved that this is a homogeneous function of degree 2. That is n equal to 2 here. Now, you should remember and recall what is your Euler's theorem. If it is homogeneous function, then we have to show that x into dou u by dou x plus y into dou u by dou y is equal to nu. So we need partial derivative with respect to x and y for u. Let's partially differentiate u with respect to x and y. The partial derivative of u with respect to x is derivative of x square is 2x plus derivative of this, which is a constant when you are differentiating with respect to x, is 0, and derivative of u with respect to y is, this is constant, therefore derivative is 0, plus derivative of y square is 2y. Now make substitution in this. X into dou u by dou x plus y into dou u by dou y is equal to x into your dou u by dou x is 2x and dou u by dou y is 2y. 2 is common factor, so if I take out 2 outside, x square plus y square will remain, but that is nothing but your u, so this is 2u and your 2 is nothing but n, so Euler's theorem is verified. In this fashion you can verify Euler's theorem. Now let's move on to next problem. Suppose if u is equal to sine inverse of x square plus y square by x plus y, then show that this is true. See, how you are going to identify that this problem can be solved using Euler's theorem? See the left hand side. Left hand side is of Euler's theorem form. So the result is of Euler's theorem form. So that's why we have to use Euler's theorem for this problem, so that you can easily get the required answer. If you want to apply Euler's theorem, it is applicable only for homogeneous function. You should remember that. Now let us verify whether your u is homogeneous or not. How? The highest power of x in the numerator. What is that? X square. Take it out. Highest power of x in the denominator. Take it out. Because we want to make this one as a function of y by x alone. Now, if you take it out, then your 1x will goes off, remaining is x into 1 plus y by x whole square divided by 1 plus y by x. Of course, this is a function of y by x, but your x should be outside, because you know it should be of the form x to the power of some power into function of y by x. But here sine inverse is there. That's why this is not a homogeneous function. You should remember, this should be of this form. Your x should be outside and remaining thing should be as one function of y by x. So that's why this is not homogeneous. That means we cannot apply Euler's theorem for this. But is it possible to reduce this one into homogeneous? Yes, it is. Why? Because this inside term of sine inverse is homogeneous. Only thing, because of this sine inverse, it is not homogeneous. Let's do one thing. Send this sine inverse to this side, so that this becomes sine u. Sine u is equal to x square plus y square by x plus y. But we have written this one as x into 1 plus y by x whole square by 1 plus y by x, which is homogeneous function of degree 1. But remember, your u is not homogeneous, but sine u, which is equal to this, is homogeneous. Let's call sine u as some phi. So phi is equal to this, which is homogeneous of degree 1, because power of x is 1. You should remember, your u is not homogeneous, but phi is homogeneous. So we can apply Euler's theorem for phi. What is that? Euler's theorem says x into dou phi by dou x plus y into dou phi by dou y is equal to n into phi. That is 1 phi. Remember, you cannot write u here because your u is not homogeneous, but phi is homogeneous. Now, differentiate this phi with respect to x. What is your phi? Your phi is sine u. What is the derivative of sine? It is cos u into, you cannot stop there only. What is the derivative of u with respect to x? It is dou u by dou x, because u is a function of x and y. And what is the partial derivative of v with respect to y? Derivative of sine u is cos u into derivative of u with respect to y is dou u by dou y. Now make substitution of these in the equation 1, so that you will get x into cos u dou u by dou x plus y into cos u dou u by dou y is equal to your phi is sine u. Now in these two, cos u is common factor, take it out, so that you will get x into dou u by dou x plus y into dou u by dou y into cos u is equal to sine u. Send this cos u to that side, so that you are going to get x into dou u by dou x plus y into dou u by dou y is equal to tan u. That is the required answer. So we have proved the problem. Now let's move on to third one. What it says, if u is equal to tan inverse of x cube plus y cube whole divided by x minus y, then show that x square into dou square u by dou x square plus 2xy into dou square u by dou x dou y plus y square into dou square u by dou y square equal to this. Remember, by seeing the left hand side of this problem, it is of the result which is same as that of Euler's extended theorem. That means we need to make use of Euler's extended theorem. But if you want to use Euler's extended theorem, we need to use Euler's theorem also. If you want to use Euler's theorem, then Euler's theorem is applicable only for homogeneous function. So let us verify homogeneity of this function u. See, u is equal to tan inverse of x cube plus y cube whole divided by x minus y. That is what the function is they are given. Now what is the highest power of x in the numerator? X cube. Let's take it out. Similarly, highest power of x is x1. So let's take it out. And x cube cancels, remaining is x square. And we can write this one as 1 plus y by x whole cube divided by 1 minus y by x. Of course, this inside function is a function of y by x to the power of some power into this function of y by x. But tan inverse is outside. Hence, this is not a homogeneous function. Is it possible to convert this one into a homogeneous function? Of course. If tan inverse was not there, then it would have been a homogeneous function. So let's send tan inverse to that side. That gives you tan u. Tan u is equal to x cube plus y cube by x minus y. But we have written this one as this. So let's call tan u as some phi. Phi is equal to tan u is equal to x cube plus y cube by x minus y. That means your phi is equal to this, which is equal to this. Therefore, this is a homogeneous function of degree 2. That means your n equal to 2. Now, by Euler's theorem, remember your u is not homogeneous, but phi is homogeneous. So, we can apply Euler's theorem for phi. X into dou phi by dou x plus y into dou phi by dou y is equal to 2 phi. But by Euler's theorem, because it is homogeneous function, we can apply Euler's theorem for phi also. X square into dou square phi by dou x square plus 2xy into dou square phi by dou x dou y plus y square into dou square phi by dou y square equal to 2 into 2 minus 1 into phi. That is n into n minus 1 into phi. Now, let's find out what is dou phi by dou x. What is your phi? Your phi is tan u. So, therefore, what is the partial derivative of phi with respect to x? Derivative of tan is secant square u into derivative of u with respect to x is dou u by dou x. But we need actually double derivative. So let's partially differentiate this again with respect to x. Now here both of these contains variables x. Therefore we need to apply product rule. Keep secant square u as it is. What is the derivative of dou u by dou x with respect to x? It is dou by dou x of dou u by dou x. That is dou square u by dou x square plus. Now keep second term as it is dou u by dou x. What is the derivative of secant square u? First you need to differentiate the power. So it is of the form x to the power of n. What is the derivative of x to the power of n? N into x to the power of n minus 1. By that way, 2 into secant to the power of 2 minus 1. 2 minus 1 is 1. So simply you will get 2 secant u. Now forget the power, because we need to apply chain rule. Forget the power. Now remaining is secant u. What is the derivative of secant u? Secant u into tan u. Now forget secant. What is remaining? U. What is the derivative of u? Dou u by dou x. But remember, in these two, secant square is common. So secant square u comes out into this much will remain. Now, remember in the Euler's extended theorem, we need dou square phi by dou x dou y. So again, partially differentiate this with respect to y. So that you will get dou square phi by dou y dou x, which is same as dou x dou y, because your function is homogeneous, is equal to. Now, here when you are partially differentiating with respect to y, this is u. You should remember this also containing u. Now apply product rule. Secant square u into partial derivative of this with respect to y, that is dou square u by dou x dou y, plus keep this one as it is. Derivative of secant square u is 2 into secant u. Derivative of secant u is secant u into tan u. Derivative of u is dou u by dou y. Now in these two, secant square u is common. Take it out. You'll get this much. We'll make all these results in we'll substitute in equation 1. Now partially differentiate phi equal to tan u with respect to y, so that dou phi by dou y is equal to tan u, derivative of tan u is secant square u, into dou u by dou y. This much you will get. Now again partially differentiate this with respect to y, because we need double derivative. So that you have to, you have to apply product rule for this. So keep first one as it is. Partial derivative of this with respect to y is dou square u by dou y square, plus keep this one as it is. Derivative of secant square u is 2 secant u. Derivative of secant u is secant u into tan u. Derivative of u with respect to y is dou u by dou y. And in these two, secant square u is common. Take it out. Now substitute all these, that is dou phi by dou x and dou phi by dou y in equation 1, in this one, and remaining things in the equation 1. Now when you substitute dou phi by dou x in this and dou phi by dou y in this, in these two, secant square is common, so secant square will comes out. See, if you take out secant square outside, remaining is x into dou u by dou x plus y into dou u by dou y. Send the secant square u to this side. That gives you 2 tan u divided by secant square u. So you should remember that your x into dou u by dou x plus y into dou u by dou y is equal to 2 times tan u by secant square u. We'll make use of this in future. Now substitute what is your dou square phi by dou x square, dou square phi by dou x dou y, dou square phi by dou y square in equation 1. So x square into, this is dou square phi by dou x square. So we have substituted. Remember here secant square u is missing. You have to write secant square u, because in all of them secant square u is present. Here, here, here. Plus 2xy into, this is dou square phi by dou x dou y. Substitute it. Plus y square into, this is dou square phi by dou y square, is equal to 2 times phi. N is 2, phi is tan u. Now in all of them secant square u is common. Remember here secant square u is missing, but you have to write secant square u. Here also secant square u is present. Here also it is present. In all three, secant square u comes out. Remaining is x square into, multiply this, x square into dou square u by dou x square plus 2x square into tan u into this plus 2xy into this plus 2xy into 2, 4xy into tan u into dou u by dou x into dou u by dou y plus y square into this plus y square into this is equal to 2 tan u. Now in all of them secant square is common, so send the secant square u to this side. That becomes 1 by secant square u. Now here we need only the terms x square into dou square u by dou x square plus 2xy into dou square u by dou x dou y plus y square into dou square u by dou y square. Send the remaining terms to that side. If you send them to that side, they all becomes minus sign. Minus 2x square tan u dou u by dou x whole square minus 4xy tan u dou u by dou x into dou u by dou y minus 2y square into tan u into dou u by dou y whole square. Now in all of this your minus 2 tan u is common, so that you left out with x square into dou u by dou x whole square plus 2xy into dou u by dou x into dou u by dou y plus y square into there. Now we can club the power of these two because both are 2. So that you will get x into dou u by dou x plus y into dou u by dou y here also. But see, that is nothing but the expansion of this a plus b whole square form. X into dou u by dou x whole square, you'll get this term, plus 2x into y into dou u by dou x into dou u by dou y, this, plus y into dou u by dou y whole square, this. So we can write this one in this form. Now you should note one thing. What is your x into dou u by dou x plus y into dou u by dou y? By above results, it is 2 tan u by secant square u. Substitute it. Now this is 2 square is 4, tan u square is tan u whole square, and this is secant square u whole square. So in these two, secant square u is common and tan u is also common, 2 is also common. So 2 tan u into 1 by secant square u comes out, remaining is 1 minus, here 2 tan u comes out, but 1 secant square u comes out, but 2 square is 4, 1 tan u whole square, that is tan square u divided by 1 secant square u has gone, so one more is remaining, secant square u. But we know that tan u is sin u by cos u and 1 by secant square u is cos square u. Tan square u is sin square u by cos square u, 1 by secant square u is cos square u. Cos square u cancel, 1 cos u cancels, so you left out with 2 sin u into cos u, which is nothing but sin 2u. So you're going to get, if you write 2 sin u into cos u as sin 2u, this one. This was the expected result. So this completes the solution of this problem. I'd given 2 more problems, work it out. One is on function having 3 independent variables, and this is a simple verification of Euler's theorem. Using Euler's theorem you need to obtain this one. See, here log is there. That is the only thing which is forcing this u not to be a homogeneous function. So if you send log to this side, it becomes e to the power of u is equal to this, and this is homogeneous function, and you call that one as a phi, that is e to the power of u is phi, and you solve this problem. Thank you.